Let's take a look at the fuel cell. Fuel cell is an electrochemical or electric cell, where the fuel is the hydrogen gas and oxygen is the oxidizing agent. So in this case, the fuel cell has the advantage of being able to fully oxidize the fuel without any combustion. So let us take a look at how this is being enabled. So when given a setup as such, the fuel at the electrode is being oxidized. Since it's being oxidized, the reaction that takes place at this electrode must be oxidation, and therefore this electrode has to be the anode. Conversely, as explained earlier, that oxygen is an oxidizing agent, which means it will reduce. Since reduction occurs at the cathode, so hence this electrode must be the cathode. The medium used for this example is alkaline. So because of that, for the half equations, we'll be looking at oxygen reducing to actually form OH minus. So hence the half equation is as such. While in the case of the anode, the half equation that is selected, where hydrogen gas is oxidized to form water in the presence of alkaline medium, in this case OH minus. Hence the standard cell potential value is 1.23 volt. The reason why the E cell value under normal circumstances is lower than 1.23 volt is because the partial pressure of oxygen is not 1 bar, since most of the time air is being used to pass through the cathode, which comprises 20% of oxygen. So in this case, the actual partial pressure of oxygen is about 0.2 bar, which is lower than 1 bar. Hence, because of this, we will expect the E reduction value to be lower than 0.4 volt. And hence, because of this, the standard cell potential will be expected to be less than 1.23 volt. The advantage of using such a setup is that certainly there isn't any unburned hydrocarbon or carbon monoxide that's been produced. And in the case of using hydrogen gas specifically as the fuel, no greenhouse gas is being produced, for example, like carbon dioxide. Okay, let's now replace the electrolyte with dilute aqueous sulfuric acid, and in this case, its concentration will be 0.5 mole per dm cube, since that will allow the concentration of H plus to be 1 mole per dm cube, given that sulfuric acid is dibasic. So with that, let's take a look at the half equations. The two half equations to consider at the cathode is these two half equations, where in both cases, oxygen actually reduces to form water and OH minus respectively. But in this case, given that the electrolyte is now changed to an acidic medium, we will be going for option 1 instead of option 2. The two half equations to consider at the anode is these two. One is the standard hydrogen electrode. The other one is where hydrogen oxidizes to form water in the presence of OH minus. Again, since the electrolyte is now sulfuric acid, we will now choose also option 1. With both option 1 that's selected, these two are now the half equations when the electrolyte becomes acidic. And what is interesting is that the E cell value also turns out to be 1.23 volt. It is important to note that it means that the E cell, the standard cell potential, remains 1.23 volt regardless of the pH of the solution. Why is this so? This is so because if you were to look at the full equations does not involve any H plus or OH minus. Hence, if we decide to change the concentration of sulfuric acid and increase it to 2 mole per dm cube, you will find that it will not affect the standard cell potential, as the standard cell potential will still remains to be 1.23 volt. And the specific explanation for that is that if we increase the concentration of H plus, the E reduction will become more positive. The E oxidation will also become more positive. But what is important is for us to note that the E cell will not change, since H plus is not part of the overall equation as indicated here. Let's now take a look at another example. This example that we are given two half equations involving oxygen, H plus, reducing to form hydrogen peroxide, and the other half equation is Cu2 plus accepting electrons to form copper. These are the two E values, and from there we can conclude the right-hand species of the higher standard electrode potential value, in this case oxygen, will undergo reduction, while copper will undergo oxidation, since its standard electrode potential value is lower. And if we are asked to draw an experimental setup to determine the cell potential, whereby the E cell value in this case will be 0.68 minus 0.34 volt. And that will give a value of 0.34 volt. So in the experimental setup, we will have copper as the electrode, concentration of Cu2 plus of 1 mole per dm cube. And the copper itself, as explained earlier, will be the anode since it oxidizes. On the other hand, we will have 1 bar of oxygen, temperature 298 Kelvin. Platinum will now be the selected electrode, since in this half equation, there isn't any metal that could be used as an electrode. The concentration of H plus and your H2O, hydrogen peroxide, both has to be 1 mole per dm cube. And that will comprise the cathode. It's important to note that we need a salt bridge. And aside to that, the reaction should proceed under a temperature of 298 Kelvin. Let's now take a look at what will happen to the E cell value if the partial pressure of oxygen decreases. If the partial pressure of oxygen decreases, then the position of equilibrium of these half equations will shift backward, which means we expect the E reduction value to decrease. And because it decreased, the E cell becomes less positive. So we expect the E cell to drop. If aqueous ammonia was slowly added to the Cu2 plus and the copper half cell, then again, Cu2 plus will form complex ion with your ammonia. Therefore, concentration of Cu2 plus will drop. And therefore, the position of equilibrium of this half equation will shift backward, which means in this case, the E oxidation will reduce. If the E oxidation reduces, then the E cell will increase or become more positive. If a smaller copper electrode were used, copper is a solid, therefore it does not shift the position of equilibrium, so there will be no change to the E cell value. If potassium manganate was slowly added to the oxygen hydrogen peroxide half cell, then we know that potassium manganate can oxidize hydrogen peroxide to form oxygen. So in this case, the concentration of your hydrogen peroxide will drop and the concentration of your oxygen would actually increase. It means the position of equilibrium will shift forward, and therefore because of that, we will expect the E reduction value to increase, and since the E reduction value increases, E cell will increase.